Should we go ahead and get started?
Sure.
Damien and I are going to co-introduce, I think.
I forgot the embarrassing slides. But
yeah.
John. This is John.
With the beard.
You know, like as always with the high-quality PhD students at Penn State, it's super exciting and humbling to be part of the committee of somebody who does all the great things that we do here. And John's really an exception, I think, in lots of ways.
Yeah, I mean, well, I think back and I remember that he first actually applied, I think, to work with Comedy. So we should probably thank her for drawing him into the program. And then I've just been amazed. I mean, so John, you know, you'll see from his thesis, he's worked on some fundamental problems that are, you know, and the work is incredibly technically sound and really creative. But on top of that, I think you guys all know, you know, he's kind of a jack of all trades in terms of, you know, he's got this, he's really engaged in geoscience education, and he's led those sessions at HEU and other meetings, and you know, he's basically started our computer user group here, or restarted that, and then, you know, there are all those other things like the blog and the infrasound that's sitting in his office, so he knows when you're opening and closing your door, and we're gonna have to, it's like an NSA kind of thing, we're gonna have to figure out who's gonna follow up on that so that we can track people in the building now. But, you know, it's just kind of an incredibly broad range of interests, and so it's really exciting to see him wrap things up, at least this chapter, I guess.
And a huge range of things that are part of his thesis, so you probably know a little bit, but there's 5 chapters in his thesis. 4 of them are already published, and the last one is probably the one he's going to focus on the most here, but one part of that is already published last year in the Nature Communications paper. And John's, you know, reached out to a broad range of the department, right? So his committee involves the 2 of us, involves Sridhar, involves Richard, and it also involves Derek Ellsworth, who couldn't be here today. And it really should involve several other people, because I know he's written several things with Chuck, who's not formally part of the committee, the other people, Don, so super impressive. And maybe we don't need to say anything on that.
No, we should probably let
turn it
him.
over to him. Falsely.
All right, so thanks for that really great introduction. I appreciate it. And I'm going to talk to you today about a dissertation which is titled Laboratory Studies of Fault Stability and Slow Earthquakes, or if you prefer an alternate title, it's How I Learned to Stop Worrying and Love the Bible. So before we get started into the science and dig in, just a couple of things. First of all, thanks for taking the time to come. I know it's the middle of defense season and semester and everybody's busy. I really appreciate it. And what I'm going to show you wouldn't have been possible without a wide range of folks, pretty much everybody in this room. Here's just some selected pictures. Of course, everybody that's on my committee, tremendous help. There were a lot of people that weren't on my committee, like Chris mentioned, Chuck, Don, a lot of folks that spent a lot of time helping me formulate my ways of thinking, develop my problem-solving skills, and just made a massive investment, and I really appreciate that. There's a lot of staff involved, as always, so our lab technician, Steve, back there in the back, spent a lot of time helping us get technical problems sorted out. And my cohort, some of which are still here in the room, others have moved on. And lastly, my family, my parents, my wife, and my in-laws continually encourage me through this. It just wouldn't have been possible without them. Okay, so I'm not going to do the traditional thing of going through this dissertation chapter by chapter. And I just wanted to let you know what's in there and show you what we're not going to talk about, but I'm happy to answer any questions about it or discuss it if somebody's interested. First of all, I did a lot on slow slip in the laboratory. That makes up 3 chapters. That's what we're going to focus on mostly. I did a little bit on slow slip in the field, particularly Willen's ice stream in Antarctica. And we'll talk about that for just a few slides at the end, because I know folks want to not be here forever. And then the first project I worked on was looking at electrical signals generated during stick slip associated with phenomena like earthquake lights and these total electron count anomalies that propagate throughout the atmosphere. But we're just not going to have time to talk about that, so if anybody wants to, I'm happy to later. Let me give you a little bit of the background, though, of what's going on here. Traditionally, this is the Cascadia subduction. So I'm just kind of a cartoon drawing here. Traditionally, we've always thought about earthquakes occurring up here in the seismogenic zone. We have some co-seismic rupture patch, dynamic rupture, shaking, all the normal things associated with an earthquake. But in the early 2000s, we started noticing that there are more interesting phenomena that occur, like episodic tremor and slip, or very low frequency earthquakes. So these occur here much deeper, much further down dip. And unfortunately, the projector's not rendering this very well, but but this is a several month period going from the cool colors to the warm colors in here of this event propagating. So it propagates much more slowly than a normal earthquake. So we wanted to see, can we explain that with laboratory observations? And that's some lab data over there we're going to look at in detail in just a little bit. All right, so there are a few fundamental questions I tried to answer. There's a whole range of questions dealing with this topic, but we had to narrow our scope somewhat. And the main one is, what parameter determines how a fault is going to fail? And preferably a physical parameter, right? We want something that's based in real hard physics. And does that match what we can determine from the theory about it? The other thing is, what sets the speed limit for these ruptures? Why do they propagate slowly? Why does the fault not just fail catastrophically? Or why does it stable slide instead of fail on either mechanism? And then, can those laboratory results be applied to the field, which is the ultimate goal? And sometimes it's a pretty big question because we're dealing with a small sample that's not necessarily in situ conditions in the lab. So what pieces of that can we take to the field and verify? How can we apply it? So we're going to take the traditional sort of three-pronged approach that I like to do these problems. I'm going to show you a couple examples from nature, actually just one for expediency's sake. Then talk about the theory behind this and go to the lab. Of course, this is the BIAX just across the hall. And at the end, we'll loop back around to nature. This is the traditional view of how faults fail. Fail in one of two mechanisms. First, it can fail stably, or creep. So here we have a plot of time and shear stress. Over time, we're loading our sample, be it in the lab or in the field, and eventually we yield rollover and stable slide. So pulling a book across the table. It's just creep. Now that doesn't mean that because it's just creep, it poses no risks. This is the California Memorial Stadium, which we all know is being sheared apart by creeping. And it also poses lots of infrastructure risks for pipes, roads, that kind of thing. Unstable failure is the one that a lot more people in this room work on. So this would be, over time, we have stress. Build up, eventually we reach some stress where the fault fails catastrophically, and all that energy is released very rapidly, tens of seconds. And that produces all kinds of shaking, right? So we have this rapid stress change. We get seismic radiation, crushing and heating, the traditional things that go into the energy budget of an earthquake, and it knocks buildings down. So that's something that we care about very much. As a very quick review, and this is going to connect in a little bit later. If we had a piece of rock, and I've got a blue marker band in here, let's say this is the initial state of the rock. As we start applying, as we start straining it, applying stress, we get deformation of that, so it's storing energy elastically. Rocks are just like springs, be it very stiff ones. And then eventually when it fails, we get this elastic rebound. This is, of course, the simplified elastic rebound hypothesis. And a nice picture to demonstrate that from 1906 earthquake, one of my favorites, before they rebuilt the fence, with the fault being very obvious there. Okay, so that's the traditional view, but we know that's not quite right. I've mentioned this earlier, that there's a gray area in the middle that all kinds of interesting behaviors are observing. So the one example we're going to look at, we're going to go to the Pacific Northwest. We've got the Juan de Fuca plate subducting beneath the North American plate. And if we look at GPS observations, the southern tip of Vancouver Island, of course, this famous plot from Rogers and Draggart, 2003, you see that we have increased eastward displacement, and then these slips back westward. So you would say, okay, this is, earthquakes are happening there, we're getting a rebound. But those slips last about 14 days. So these are much slower, though they're releasing about a magnitude 7's worth of energy. And they occur every 14 months. They're actually very regular. You'll notice down here, this black line represents the average tremor activity over a 10-hour period, but they're accompanied with large bursts of tremor as well. So to get at why this is happening, we need to understand what makes a fault stable or unstable or somewhere in between. There are two key components. First of all, it has to have a velocity weakening behavior. We'll talk a little bit more about what that means in a second for those of you not familiar with rate and state. And it has to have, I say, adequate system compliance. That's what we would say in the lab. It just has to be a sufficiently de-stiffened system. So whatever you consider the stiffness of the fault zone. Right, so a little bit about the velocity weakening bit. We've got three plots here. Displacement, you could think of it as time as well, probably. And friction. And what we're doing is we're sliding at one velocity here, and then we rapidly increase the velocity, so say from 1 to 10 microns a second. And you see there's a dynamic response, and then a new steady state value of friction. So friction isn't just this simple static or dynamic quantity, it changes with velocity. Rate weakening would be the faster we go, the weaker it gets, the lower the value of friction, and we would say the frictional parameters A minus B are less than 0. On the other end of the spectrum, faster we go, stronger it gets, A minus B greater than 0, it's velocity strengthening. And of course, the middle would be velocity neutral, which you can get things close, but generally they're one way or the other slightly. You can see why we have to be velocity weakening to get some kind of unstable failure. If the faster we shear, as we try to propagate some kind of rupture, it just gets stronger. Eventually we're going to arrest that rupture. The second part of the puzzle isn't quite as clear. This is the part about the system compliance, or the stiffness. So if we look at a simplified model, this is the spring slider classic model. So we have a surface, we have a slider, this would represent the fault, a spring representing the elastic rocks or elastic fault zone, and a motor representing movement or whatever's loading your system. If we pull it and that spring is sufficiently stiff, it's going to slide in a stable manner. But if it's less stiff than some critical stiffness, which we'll talk about a lot during the talk, that we can define in terms of rate and state parameters, it'll behave in an unstable way. The reason this is, if we have to have the fault weaken faster than energy can be unloaded into the system. So this would represent the unloading stiffness, the force per displacement of the spring, and here you see the faults weakening faster, so all this green area is energy available to accelerate the system. Now, I want to point out this doesn't only apply to earthquakes. We can connect this to the engineering literature in a lot of ways. In fact, it was only in 1966 that stick slip was really said this is an analog for earthquakes. Engineers have cared about this for a long time for a number of reasons, one of which being tool chatter when we're doing industrial operations. In fact, if you look in the engineering literature and look at some of the tool chatter papers, this looks pretty familiar. We have elastic elements. We're trying to make sure that this is a sufficiently stiff system so that we get accurate machining. Also in Nature, this is a paper about lobsters making noise with their scales, and you can see again we have elastic elements, and it has to be sufficiently compliant for them to be able to stick slip and make the noise. Some of the very early literature regarding this actually dealt with friction of paper, which may seem like a not very important topic, but anybody that's dealt with a human day, a printer, knows that paper friction is actually something that printer manufacturers care a significant amount about. All right, so I'm going to show you a lot of things about stiffness and critical stiffness, and just want to remind you that the traditional Huxley way of looking at this is force is the stiffness times the displacement. Well, in the lab, we're applying a shear stress and some load point displacement with this hydraulic piston that I'll show you. So I'm going to call that delta S sub LP, and then shear stress. And if we divide through by normal stress, that gives us a friction. So all the stiffnesses I'll show you are friction per displacement. You can think of it as force per displacement. Same idea, we just normalize it. Okay, so now we're going to dig into some of these terms. Here we've got the critical stiffness divided by the normal stress equals these frictional parameters, the critical slip distance and B minus A, or the rate parameter. It's easier to talk about whether the fault's going to be stable or unstable by using the ratio of the stiffness to the critical stiffness. So K over K sub C, we're going to call that kappa. So if kappa is less than 1, we're going to be in an unstable system. We expect stick slip. If it's greater than 1, we expect the system to behave in a stable manner. So what parameters in this equation can we change, can we modify? Well, stiffness is something that we can control in the laboratory, as is normal stress. Now, the frictional parameters are a little bit trickier. We can change the material that we're using. We can't necessarily control the frictional parameters of a given material, but we can try different materials. But the critical stiffness is something that's defined by these things as is kappa, so we just have to live with the values that we're getting there. So again, the traditional view, kappa, K over K sub C. Above 1, we're stable. Below 1, we're unstable. And this is for any perturbation size. No matter how hard we kick the system, if we're above 1, it's going to be stable. But we know that that's not really the case from our observations. What I'm going to try to convince you of is that the stability field probably looks a little bit more like this. So above 1, we're stable unless we're kicking the system really hard. We're putting out a very large perturbation. Far below 1, for any perturbation size, or no perturbation practically, we're going to be unstable. So we'll get stick-slip behavior. But when we're close to 1 and for small perturbations, we're going to be in this quasi-dynamic realm of slip. So not quite stable, not quite unstable. Near the stability boundary, there have been some scattered observations of this kind of behavior. So Schultz in 72 showed these slow displacements, some experiments. Bomberger and his co-workers in 94 also show a transition from stable to unstable. And Madakari in 2015, shearing some natural samples, actually saw a couple of slow stabilities, nucleate as well. But there hasn't really been a systematic study going through this and trying to determine parameter by parameter what's happening. So that's what I spent a lot of time working on. So we've used the BIAX. Again, this is just a blown up picture of it. It's required for every talk. And we'll go over a little bit of the setup here. There's the BIAX, banana for scale. At the end of each of these 1 meganewton hydraulic pistons, we have load cells that allow us to measure the force that we're putting on the sample. DCDTs, or displacement transducers, allow us to measure where each piston is and control either the load or the displacement of that piston. And inside that load frame, so in this little red box, we build this sample. This is a powder sandwich. We've got 2 side blocks and a center block that are generally made out of steel or titanium. We apply a normal stress, let the sample compact, we keep the normal stress constant, and then we shear the center block down by driving at a constant rate. And I will show you that with this animation. It's made at great expense. So we can shear about 50 millimeters. This is what that setup actually looks like. So it's, of course, a little bit messier than the nice Illustrator drawing. But we've added a lot of additional instrumentation, most of which I'm not going to have time, again, to talk about. But we can add displacement transducers directly on this center block. So we're measuring the displacement on the fault in the laboratory. We've been able to measure shear heating by embedding thermistors in the side of the blocks. We can also measure acoustic travel time as well. It's something that Jacques Riviere has been working on a lot. So how are we going to explore this space? What we want to do is map out and prove to ourselves that this conceptual model is what's really happening in terms of fault stability. The first thing that's easy to change with the BIAX is going to be K. So when Chris designed the BIAX, he wanted it to be very stiff because they wanted to do these velocity step tests. Like I showed you earlier, you need a stiff system because you need to be stable sliding. And he did a very good job of doing that, and then we spent a while trying to figure out how to undo that. And we came up with a couple of ways. First of all, I said we normally make all of these blocks out of steel or titanium. Well, we can put an identical block, I've got one here, it's got the teeth on it, just like our regular blocks and everything, but made out of acrylic or PMMA or other plastics to de-stiffen the system. If you think about what this looks like, the red patch represents where the fault is in the laboratory, our 10 centimeter by 10 centimeter patch. And we have these compliant elements all along the loading path. It's one big elastic block. Another way that we experimented with, and didn't do as much of, I'll primarily show this, is we have an elastic element above the fault zone. So we just put a piece of acrylic or something to de-stiffen the system on top of these steel blocks. But that's a little bit different. We don't have a compliant block directly coupled into the fault zone. We have the steel with some compliance above it. We can only do so much, though, because we have to live with the materials that will handle the stress that we're going to put on them. Acrylic turned out to be the best choice. But the idea being we decrease K, which means the kappa goes down, we're more unstable. So we're pushing ourselves to the left on that plot. Okay, now normal stress. This is another thing that we can change in the laboratory very easily. It's actually nice because it's literally a knob that we can turn. People say that about models all the time. But if we increase the normal stress, that means our critical stiffness is going to go up. Just move that to the right side. Kc goes up, K goes down. So as we increase the normal stress, we become more unstable. So now we know how to modify the stiffness of the system in 2 ways. Normal stress, or the stiffness ratio. Normal stress, and by changing these blocks, we have to measure it. And we need to measure it very carefully. So one way to do this will be, as we're shearing along, we stop, we unload and reload the shear stress on the system. And we pick some range, in this case friction of 0.3 to 0.4, fit a line to that data, and that gives you a friction per displacement, which we proved earlier is a stiffness. But unfortunately, as you can see, when you do these unload reloads, there's some memory effects, so this data may not be representative of what's happening with the stick slips and slow slips, and it interrupts our experiment. We'd like to have some cleaner plots. If it's stable, we have to do that. But if it's unstable, if we have stick slip events, we can fit this load up portion of each individual event. We again get a friction per displacement, we get a stiffness. Now we have the problem if we've got two ways to measure stiffness. We want to make sure we're comparing, not comparing apples to oranges or anything here. So we ran this experiment. The gray dots represent the stiffnesses obtained from these unload reloads. The blue dots represent the stiffnesses obtained from each individual stick slip event. As you can see, they correspond very well. It's a very small difference there if you look at the scale. So now we've convinced ourselves that's fine. We can go on and explore this space. Through a set of coincidences dealing with the first project on fault electrostatics, we started working with this material. Got an SEM image over here, and if I didn't tell you what it was, I think we would make guesses like quartz. And that's baking flour, like you would make a cake with. And so we started shearing this, and we sheared it in a couple of different setups. We used an all steel setup, then we used a block set that was steel on the side blocks with an acrylic center block, much like the one I brought, and then all acrylic, so acrylic side blocks and an acrylic center block. So we're going from least compliant to most compliant. As you can see, we transition from stable sliding to unstable, and as we become more compliant, the events become larger. So that was really fascinating, that we could take this one material, not change anything else other than the stiffness of the system, and traverse that boundary, though this was traversing it in a rather coarse way. But we said, well, we can, now that it's stable sliding, we can actually measure K sub C and try to figure out, is this K over K sub C or kappa value where this transition's happening consistent with what we know from theory? So we did these velocity steps. The gray point to the data, black line is a model, much like I showed you before, and we could measure B minus A and D sub C. We know the normal stress, we can calculate our critical stiffness. Well, we thought that was very interesting, published that, and of course, we know that fault zones aren't filled with flour. So we wanted to work with a more geologic material. We wanted to explore the range of what would happen with other materials. So we started using this material. It's called Minisil. This is an engineering material. It's very consistent. We can get it in 5-gallon buckets, very highly quality controlled. It's particle size distribution up here. We've got a mean grain size of about 10 microns, and it's basically crushed quartz. You can see what it looks like there in the SCM. We get very, very reproducible results with this material as long as we control the humidity of the experiment. Unfortunately, Minisil was very hard to get it to do a velocity step test, have something we can nicely model. We're too close to the stability boundary, even in all steel. So we measured the frictional parameter A minus B in a little bit of an old school way. We just sheared at many, many velocities at different normal stresses. And we get this plot, and the slope of this line is A minus B, so we have a value of about minus 0.02 here. As data looks very scattered because you're looking at many experiments and many normal stresses. If we show just a couple of normal stresses, which we will later, you'll see that it lines up very nicely. What we also observed was that as we increased normal stress, A minus B became more negative. So we're becoming more velocity weakening as we increase normal stress. Increasing normal stress by itself makes us more unstable. Decreasing A minus B makes us more unstable. So now we have two confounding factors making our system more unstable as we increase the normal stress. After some playing with the system, trying to figure out where we were in stability space to start with, we were able to generate these really nice slow slip events in Minisil. This is a portion of an experiment. We load up and we begin sliding. You see we stable slide for about 10 millimeters. And then, spontaneously, you can see in this zoom, we're not changing anything. We're shearing at 10 microns a second the whole time. We begin to get slow slip events that start up spontaneously. So they start very small and very slow and grow over a couple dozen cycles. You can see if we zoom in again, 3 of those, that the slip velocity is reaching tens of microns a second, so just a few times what we're pushing it. Considering that in the lab when we get fast stick slip, what we consider to be earthquake analogs, they last a few hundredths of a second and slip at millimeters a second. This is incredibly slow. You can see that the scale bar is 2 seconds there. So now that we had our system tuned and we know where we were in stability space, we varied the normal stress from 6 to 14 megapascals. So up here we have a kappa of about 0.7, meaning that we're far to the left on that plot, it's an unstable field. Down here we have a kappa of about 0.99. So we're right on the edge of the stability boundary. In fact, you can see that the events will sometimes die out and will stable slide for a very short amount of time. There's a lot of interesting systematics in the plot that we're not going to have a lot of time to discuss, such as the change in onset, and of course they get faster, as I'll show you as we become less stable. This plot has many, many experiments on it, and it's a little dense, so we'll go through it a little bit more slowly. Each of the black dots is an experiment that was stable sliding, and we had to do the unload, reload cycles on to obtain the stiffness. That's why it's more sparsely sampled. All of those stable sliding. All of the red dots are stiffnesses obtained from individual stick slip or slow slip events. So those were unstable. And you see that there's a pretty nice division between the black dots and the red dots just in the raw data. If we calculate what the critical stiffness should be based on what we know about the frictional parameters of this material, we get something like the black line. So the theory already does a pretty good job of separating stable and unstable. If we zoom in on this steady state section, the unstable plot, we color each dot, each event, by the peak slip velocity. So going from a few tens of microns a second up to 4.5 millimeters a second, you see that the further we are below the stability boundary, that kappa plotted here, further we are below 1, the more the colors tend towards blue. So the faster it is. Makes sense, right? The further below the boundary, we should be more unstable. So we're getting higher peak slip velocities, more like an earthquake. But it's not a sharp division. We're not saying we have slow slip events, sharp division, then we're going very fast earthquakes. It's a gradation. In fact, if we take some averages, that's what the larger dots are, and then each one of these being an individual stick slip event, looking at the friction drop and the peak slip velocity of these experiments, as we increase the normal stress, become more unstable, we get larger friction drops and larger peak slip velocities. So we're going up to about 5 millimeters a second there, and friction drops up to about 0.05. What's interesting in this data is that the slow friction drops seem to not have a stronger trend. There's more of a flat section. Now, if we look at this onset in these experiments, so now we're looking very early on, about 10 millimeters shear displacement. Here we see the spontaneous onset that we talked about. This is the displacement. You see detrended each fault slip. We can take some derivatives, which is always dangerous to do with real data, and look at the velocity and the acceleration. We see peak velocities increasing, and we see the accelerations making those nice kind of sigmoidal patterns. If we look at it in phase space, which if you haven't seen it before, is a little strange, we're looking at the log of the velocity that the fault is moving divided by the velocity that we're pushing at. So over here, fault's moving faster than we're pushing. Over here, fault's moving slower than we're pushing. And on the y-axis, we have friction. You see that we start here in the center, we're driving, and we're sliding at the same velocity. And then as these events nucleate, we spiral outward in phase space. Now, if we run a model, this is a very simple rate and state model. It's one state variable, it has no inertia, there's no fancy things in it at all, just a textbook version. And we play with the parameter sum to try to see if we can make something that looks like that. For a kappa of just below 1, you can induce a small perturbation and get this growing behavior. We see a very similar displacement curve. Velocities, it's all on the same scale. And the acceleration curve even looks very similar. And what we did notice is the model takes more cycles to spin up to the same peak slip velocity than the experiment did. But in phase space, you see, well, it looks pretty similar. So that simple model did a decent job, which was surprising to us. Of course, if you keep running this model, eventually, since k over k sub c is less than 1 and there's no inertia, it becomes fully dynamic and it blows up numerically. So you can't do that. Now, what about later on in the experiment, when we're getting slow slip events, they're not changing much. We're just getting these nice repeated events that are very consistent. They look like up here. Here we've got 4 of the slip events, velocity plot showing they're going up to about 60 microns a second when we're driving at 10. Now we're making the same phase plot. There are 2 different DC-DTs in this experiment, one at the top and one at the bottom of the fault. I'm not going to go into all the intricacies there, but let's look at the bottom one, the green curve. And you see that we're locked, we load, and then we slip. We just keep repeating the same loop in phase space over and over and over again. We're caught in the limit cycle. If we run the same model, but we set K over K sub C to be exactly 1, and then we apply a perturbation, we get very similar behavior. We're repeating in a limit cycle, we get peak slip velocities that are similar, but our locking is not nearly as effective. We rarely go much below what we're driving at in the model. So how can we explain what we see in the experiments then? We start out, we have these growing instabilities, and then they stop growing. Well, one explanation would be that K over K sub C is changing. As we're shearing during the experiment, we're developing a fabric in the layer, we're modifying the stiffness. So initially we could have a K over K sub C of less than 1. We get these instabilities that begin to grow. As the stiffness of the system increases and approaches the critical stiffness, in some cases, we can become locked in one of these limit cycles where we're just going around and around in phase space. So that's all at 10 microns a second, everything that you've seen so far in terms of what the velocity we sheared at. We then tried shearing at different velocities to say, well, is there any velocity component to the stability of the fault zone? Well, as it turns out, here we're shearing at 30 microns a second, and we increase up to 350. You see we're sliding stably here, drop the velocity back down to 10 microns a second, and our slow slip events come back. So looking at this, we say, yes, there is some kind of velocity component to this story. As the fault begins to slip faster, it looks like where it's at, its stability is changing. So again, ran another large suite of experiments, a subset of which is here. We're looking at 3 different normal stresses, 5, 7, and 12 MPa, so we're becoming less stable as you go to the right. And then we ran at a range of velocities from 3 to 300 microns a second. This is for the entire experiments. Each of these experiments, 1 normal stress, 1 velocity condition. What we see is as we go faster, looking at the 7 megapascal column specifically, we become stable. Over here, it's becoming smaller. Here, we barely have any kind of little instability there. And at 7 megapascals and 100 microns per second, we ran 2 experiments. We're right on the edge. We're K over K sub C of 1 there. You can see in one of them, we slid stably, and one of them we had small events that would come in and go away. So we're right on the edge of the boundary. So that in itself is a pretty interesting set of observations. If we plot the peak slip velocity normalized by the driving velocity, so we kind of deconvolve those 2 things, you see that as we become more stable, we go to higher velocities, that drops down until that ratio is 1, we're sliding stably, and the friction drop also decreases with the log of velocity, as we would expect. There's a lot of ways to view this data set because we did multiple velocities, multiple normal stresses. We're going to mostly focus on the right plot here, where we have velocity, log velocity on the x-axis, normal stress on the y, so this is our matrix of experimental conditions, you could say. And then those dots are colored by the friction drop that we saw there, the size of the earthquake. So the darker colors are larger. The light colors, this is measured by just taking the peak and trough of these segments of data. So those are actually stable sliding. It's just the little bit of noise that we have in our measurements. Remember, we're looking at the 4th and 5th decimal place here. So you can see that there's a pretty clear division in terms of as we go slower and to higher normal stresses, we're in this unstable realm. And the shape of this is a little bit tricky to define. Is it a straight line or is there some curve to it? Knowing that friction drop changes with the log of velocity, we would expect it to be a little bit more of a straight line. So now we have to answer the question, what is changing? We know this equation is telling us about the stability of the fault, K over K sub C. So what's changing with increasing velocity that's modifying behavior of the system? Well, there are 2 options. K goes up or K sub C goes down. Let's look at the first option. After one of these experiments, we ran unload, reload cycles to see, at different velocities, to see if the stiffness of the system changes. And there's a slight increase in the stiffness of the system as we increase the velocity that we're shearing. Now, this is very small. It's actually not enough to push us around in stability space, so I'll demonstrate in a little bit. But there is an increase, and it's in the right sign. Now, the other option is that K sub C has to go down. And we know that K sub C is defined by this equation. So either B minus A has to go down or D sub C has to go up. But B minus A going down. Here's where we're going to come back to some of that data that I talked about earlier. I said there's a lot of scatter later. We're looking at friction at different velocities. The black dots are measurements. If A minus B is constant with velocity, this will be a straight line. There's a black line right there that represents that. If we allow A minus B to change with velocity, so we're going more towards velocity neutral or velocity strengthening as we increase velocity, you can see that it's a very small change on this plot. We couldn't rule it out with the scatter in our data. And this change, though small, is enough to push us around in stability space. Okay, so we've got all of those options covered except D sub C now. We need D sub C to increase with the velocity to make this work. And there is some data, again, we couldn't get stable sliding in our experimental setup, but there's some data that Karen Mayer and Chris published in 1999 showing that in a similar material, increase in velocity can result in a pretty dramatic increase in D sub C. So again, there's evidence that A minus B and D sub C operate in the right sign. So what's turning out to show us is that stability space is this really high dimensional problem. It's not as simple as what's the stiffness of the fault zone, what are its material properties. There's velocity dependence to all of these things. So you've got stiffness, you've got velocity, and then your favorite frictional parameter on that axis. Let's do a little bit of a sensitivity analysis here and see how sensitive each of these parameters is going to be. Here we have a plot of A minus B and D sub C. These contour lines represent kappa. So below 1, unstable, above 1, stable, slow slip in this regime. Let's zoom in on this little red box over here on the right. So remember, we're looking at 0.005 in A minus B and just 4 microns in D sub C on this axis. Very small ranges. Assuming we have an experiment that starts here in the unstable realm, we're getting fast stick slip. What would it take for us to go through slow slip all the way to stable sliding? As it turns out, about a micron and a half change in D sub C would be sufficient. Just very, very small. Very easy to accomplish. Crush grains, all kinds of things. A minus B, again, about 0.001 change in A minus B, which is consistent with those plots I showed you earlier, saying we have a hard time constraining whether that velocity change exists over our range of measurement. If we allow both to change, which we have some evidence for happening, we can take this middle trajectory here, where even smaller changes in D sub C and A minus B can take us all the way from fast, slow, to stable. So it's very sensitive to all of these parameters. Okay, so a little bit of a summary table on the lab work, and then we'll very briefly touch on the field. Stiffness, we can control absolutely in the lab. We can add a spring in one way or another, and we can control normal stress. You can think there's pore pressure in the field, variations in normal stress in the lab, and we can change the frictional parameters by changing the material or by using the same material and changing the velocity. So we can make a really high resolution map of this space, and I hope that I've convinced you that we've done that for this particular material. But that's great. We've done all this lab work. Does it mean anything when we look at a field setting, or can we make some conjectures about what could be happening in a field setting? This is Willem's ice stream down here in Antarctica. We have very fast-moving surface ice. About 90% of the interior accumulation is getting discharged through 10% of the coastal area. So you see we've got ice velocities of several hundred meters per year. And in 1989, there was an expedition that took samples of the till the ice stream is sliding on up here on this tributary of the ice stream. Done a lot of work on this ice stream. It's very interesting. Sridhar has done a lot of work here. This is some data that he collected in 2003, showing that the ice stream is not just sliding in a stable way, but over time, so we've got several days here, and the displacement of the GPS station on the y-axis, we see a familiar pattern. It looks like the lab data or the natural data. We're stuck, and then there's a slip, stick, and then slip over and over. Each of these slips lasts about 30 minutes or so, and we're slipping half a meter to a meter. Generally, every 12 hours there's a slip. Sometimes there's a skipped cycle. We can go 24, and the slip is larger, just like we would expect. This is an ideal natural laboratory to look at slow slipping, because slow slip's happening every 12 to 24 hours. And it's, only, I say in quotes only, because there's a massive logistical challenge to doing this, but it's only below a kilometer of ice as compared to tens of kilometers of rock offshore where it's hard to access. Still hard to access though. These are some pictures I like to show of when they did the drilling operations. So the hot water drills melt through the kilometer of ice and use a piston core to take the samples. There's a little bit of work done on these samples and they're in storage until we got a hold of them a couple years ago. This is an example of one of them that we have sections so you can see what's inside. There are some clasts. Mostly there's a large amount of clays, and generally a mudstone type texture. We were able to put these in the Timco pressure vessels, so triaxial pressure vessels, and do all kinds of experiments I'm not going to have time again to go into, other than to say we squeeze them in tidal ways, we squeeze them in step loading ways, and we measure the porosity, the permeability, compressibility, and acoustic velocity of these samples at these different stresses. We can come up with a model that says, why does Willans keep slow slipping? How does it do this? Why does it not just dynamically rupture? Why does eventually the till not get so churned up that it stick slips in a rapid way? Let's imagine that we are starting during a slip cycle. The ice is sliding, we're dilating the till, we're tearing things up, we're de-stiffening the system. So K is becoming much less than K sub C. We've run out of energy, and the system is now stuck. So we're reloading. K is less than K sub C, we're far into the unstable realm. As we reload, we're doing things like closing of cracks, processes we would expect to happen on normal fault zones as well. And we can consider this as a normal fault zone, because physics is physics. It should work anywhere we're doing it, regardless of the material or where it is. So we're closing these cracks, we're increasing K. K's approaching K sub C now, was much less. We're increasing K. And now it comes time to slip again. K is very close to K sub C. So we're going in a slow slip manner. There's a lot of future directions that this work could go. We've answered some of the questions that we set out to. Get to that in just a second, but a few things I think would be interesting to look at are the heat generation. Here's a plot of temperature anomaly during these slow slips in the lab. You can see these little 1 millikelvin anomalies that we measure. So what's going on there? Can we accurately model that? Looking at the acoustic spectra, these events, running some more complicated rate and state models that actually incorporate the velocity dependence of all these parameters that I described, incorporate things like inertia that we know are important for large-scale systems, and then determination of a mechanism for this designer friction. So why does A minus B and D sub C change with velocity? We need a good physical understanding of that. Okay, so in summary, these are the fundamental questions that we set out to answer, so let's see how we did. Physical parameters that determine how a fault zone is going to fail. Does that match theory? We know that kappa, or the critical stiffness ratio, is a good descriptor, and it does a pretty good job of matching theory when we start accounting for things like velocity dependence of A minus B, D sub C, and so on. What sets the speed limit? Well, it could be this change in these parameters as the fault zone begins to slide faster. It gets closer and closer to stable, so we're limiting the rupture speed that can happen. Can our laboratory results be applied to a field setting? We looked at a very short snippet of Willans ice stream. We showed you that by using the logic we determined in the lab, we could come up with a plausible explanation for why the ice stream has repeatedly slow slipped. So with that, I'd like to thank you for coming and taking the time. I'm happy to answer any questions.
Hey, John, a great presentation. So lots of questions certainly. So you talked about subduction zone, you talked about laboratory experience of ice slipping. So you've got 3 very different temperatures, 3 different engineering materials, 3 different fracture roughnesses perhaps. You can talk about whatever you want about that, but in particular I'm kind of curious, these very different settings and they all show the same type of behavior. What do you think is going on at at that grain-grain boundary at the fracture that makes these three systems so similar in this way?
That's a good question. They are very dissimilar systems. And I guess I'll go back to an earlier comment about physics is physics and it should work anywhere, right? So if we understand from an energy balance standpoint that we can unload energy into the system at a certain rate, and the system is going to weaken at a certain rate, regardless of whether we're dealing with an ice-till boundary at a lower temperature or subduction zone at a higher temperature, the same physics should work, right? We should have to have the right material properties and the right stiffness of the system to be able to do it. So I look at it from an energy balance standpoint, not necessarily a micromechanics standpoint.
If I understood correctly, the mechanism for changing the stiffness as the instability progresses was dilation in the ice case, and it's been argued that dilation can result in hardening through increases in effective normal stress.
Right.
And so, I mean, is this? I mean, because, you know, so there's another effect from dilation that could actually arrest these things after they get going as well. I mean, do you have any comments on that? Or?
Yeah, I mean, it's something we didn't examine right in the laboratory experiments at all, but as you dilate and you're increasing the pore volume, keeping the same amount of fluid in there, you're decreasing the fluid pressure and increasing the effective normal stress. So that could certainly be one factor. Another factor that I didn't really mention as much in there, but let's say that you have your rupture as property, you could be generating new cracks as well as de-stiffening the system. To do that, we'd have to do these experiments inside pressure vessel. We can measure what's going on with the pore pressure. In fact, getting the normal displacements in these experiments turned out to be a little tricky because of our confined element in the center. So that's why I didn't really look at dilation as much. It's a great point.
So in subduction zones, I'm thinking specifically, where we see most of these solicit phenomena is down dip of the seismogenic zone, but also up dip of the seismogenic zone.
Right.
And I'm thinking in those spots, we often not only consider a frictional difference, but those spots we can think of as not totally elastic. And so you've talked about this system, it's entirely elastic, but when you start incorporating volume deformation effects, plasticity, viscosity, things like that, how do you see that affecting these results?
Yeah, so if you had some inelastic deformation, which during the experiments, I showed you measuring the stiffness of the system, calling it the linear elastic stiffness, by taking the slope of one of these events. Well, during that event, from our onboard measurements, we know the fault isn't perfectly stationary. So we do have some inelastic things happening here, even if they're not necessarily a plastic process. Again, I think that'd be something to do in a whole other suite of tests, or again, a more complicated model.
Almost a PhD.
Yes, a whole other PhD. But in terms of this, the linear elastic relation works surprisingly well. So I think that says something about the level of contribution of linear elastic.
In your in the beginning, you're talking about a cartoon about velocity weakening. And I think, and in that case, it looked like there was kind of an overshoot of weakening and then adjustment to a weaker state.
Right.
Is that just a cartoon, or do you observe that in your experiments too? That there's an over weakening that then is stabilized?
We can observe that in experiments as well. So it depends on how close you are to being unstable. There's an overshoot. If you're in a very stable system, you can just go right to the new state. There's no overshoot at all.
Right.
The limit of that would be that overshoot keeps happening and you've got stick-slip events.
Okay.
And in fact, in some of our, so we couldn't get the rate of state properties of Minisil because the velocity steps were marginally unstable. When we would do those velocity steps, instead of just a little bit of overshoot, we actually would have one stick-slip event occur and then a new steady state slide of friction. So it's a function of how close you are to the stability boundary. Where you get that overshoot, or you can even get ringing afterwards.
Sorry, I have another one. So you were talking about the issues of this sort of velocity dependence of these characteristics, and you sort of, I think you threw in crushed grains as a potential mechanism.
Mm-hmm.
I don't really care what the mechanism is particularly, but I'm curious if there's a hysteresis there. If there's once you change the system, you permanently change it, or once you know going back and forth in velocity, you would jump across that stability boundary there.
Well, so what we observed in that experiment where we changed velocity multiple times in one experiment was we could jump back and forth. Now, at these normal stresses, I'm not crushing grains.
Right, right.
14 megapascals and below, we don't have significant crushing of grains anyway. So that mechanism maybe doesn't permanently change things. I mentioned at the end coming up with a physical mechanism for this designer friction. One of the interesting things, and part of why it tied in to the temperature measurements, is we know that temperature can change the rate state parameters. So are we having local changes in those parameters due to shear heating, for example, which would be a possibility.
So, sort of to piggyback on that, the naive question would have been, you showed the grain size distribution for mini cell, and you see the same grain size distribution after the experiments?
Yes, we did multiple of the normal stress experiments we remeasured after we sheared, and we saw a minimal grain size reduction. So we didn't have any significant, which is expected for this range of stress. Marco Scuderi has done some other experiments at much higher normal stresses with significant grain crushing, and has seen all kinds of interesting effects there, though.
Is the Willis ice stream data, is it special, or is there a slow slip area that's embedded in some larger piece that's doing something else? Do you know?
Yeah, so I mean, on bulk, the ice
Yeah.
stream is locked most of the time and has these slip events. But there's some interesting GPS data, which I didn't have the movie for time to show, but showing that it's a slip patch that starts upstream and actually propagates, so we can track the movement of a slip patch on the ice stream. And in fact, they could see that when they drilled the borehole as well. After they drilled it, they waited for one of these slip fronts to pass, so the ice moved to fresh till, so they were able to observe that.
Well, all right, you made believers out of them.
Should thank John
Thanks,
again.
John. Yeah, we'll take a quick break and then the committee will convene. Can we turn the lights on there?
Yeah. Too much time in the dark, not good.
So are you recording that or?